All right, kids. AP Physics students. So with you guys, I need to go over one more equation on the thermal side. And if you look on your, hold on. This is actually on the purple sheet. So on this purple sheet, you've got this equation that's down here towards this left side. And you have Q over delta T equals Ka delta T over L. Okay, and this is where all this is like where you have the ideal gas law, PV equals nRT. And there's some other equations that we're going to have. So for you guys, you're going to have to shift to this purple sheet to find these equations. Because in the AP Physics world, this is actually in AP Physics 2. So this is why these equations are here on this purple sheet. So with that said, here's the deal. So what this is Q is going to be your thermal energy. So this is joules per second. So this is how much energy is radiated across a wall or a barrier of some kind. So this is your cross-sectional area. This is your change in temperature. So this is your temperature variant between one side and the other. So like let's say it's really, really cold outside. So you would have a big gradient temperature across here. So if it's like, 20 degrees outside and you want it to be 70 degrees inside your house, that's a big gradient temperature. And this has to be in Celsius, by the way. And this L is going to be the thickness of the wall. So if you look in your book and on page, hold on. Because this is going to be from your assignment. Give me a second. So you have this question down here on number 19. I realize that this is small, but if you look on page 385 of your book, all right, so I have that book handy. And if you look on page 385, it has these lists of constants for K. And it's called, on page 385, these thermal conductivity measures. And it has weird units. So the units of K, go back here, are watts per meter Kelvin. Now, here's the reason why this works. So this is thermal energy lost per unit of time. So that's thermal, it's energy, so that's joules per second. Joules per second is the same thing as watts. Now, this is where the units get a little bit weird. So this is your area, so that's in meters squared. This is L, this is your thickness, which is going to be in meters, and then you have your change in temperature, which is going to be in Kelvin. Now, I want to point out one thing. If you go from 10 degrees Celsius to 20 degrees Celsius, okay, that's the temperature change of 10 degrees Celsius. If you look at Kelvin, well, that would be 283 Kelvin. And 20 degrees would be 293 Kelvin, which is also the same change. So because this is change in temperature, it doesn't make any difference if it's in Celsius or Kelvin, because a 10-degree change in Kelvin is the same as a 10-degree change in Celsius. Yes, ma'am?
I was listening.
Okay, all right. So hopefully this equation makes sense. So if you look at this, this is your cross-sectional area. So if you have a bigger wall, then that's going to be directly proportional to this rate of energy loss. So the bigger this area is, the more you have capacity to lose thermal energy. This is the thickness of the wall. So because you're dividing by this, so clearly the thicker that wall is, that's going to reduce that thermal energy. So if you ever build a house, typically most houses are built with
All students, please report to your Encore at this time. All students report to Encore at this time.
So if you have a 2x4 wall, okay, versus if you could also build it with like a 2x6 wall. So if you build it with a 2x6 wall, that's going to be a thicker wall. You're going to divide by a bigger number. That's going to create a smaller radiant heat loss across that barrier. So, and also look at this change in temperature. So the bigger the change in temperature is between one side of the wall and the other, the bigger that heat loss is going to be. Now, think about this. If there is no change in temperature, okay, if it's the same temperature on both sides of the wall, there is no thermal energy loss because there is no change in temperature. So, this is the last problem on there. I just want you to be familiar with this equation. You're going to look at these different values of K, and if you look at that, you'll see that, like diamond, okay, has a very, very high rate of thermal loss. So diamonds actually transfer energy very, very easily. But if you look at like the smallest one on this chart, air, air has a very, very, very small thermal barrier or small thermal constant. So air is actually a very, very good insulator. So that's why when windows, they'll have like a vapor barrier between the panes of the windows, because that isn't going to transfer that energy very easily. Now, I got to stop this because I got to do encore. I'll get back with you in just a second.